Hello students, in this video we'll see how the eigenvalue problem can help us to diagonalize a matrix. Let's suppose that A is a 2 by 2 matrix. Okay. This will generalize to n by n matrix as well, with eigenvalues lambda 1 not equal to lambda 2, not equal to 0. Okay. Man, I messed up again. Great job, Mike. Hello students, in this video we'll see how the eigenvalue problem can help us to diagonalize a matrix. Let's suppose A is an n by n matrix and A of Vj is equal to lambda j Vj. Like so. So in other words, for j going between 1 and n. And let's just suppose for simplicity that these eigenvalues are distinct. They don't need to be, but for simplicity of like them distinct, where the eigenvalues are distinct. And in this case we can show that the eigenvectors will be linearly independent. Then okay, so I have distinct eigenvalues, so I'll get independent eigenvectors, okay? And so what this tells me over here is what I'm going to do now is I'm going to form a matrix P, so form P, which is the matrix V1 in the first column, V2, all the way down to Vn. So I form a column vector where the eigenvectors are my columns. And then what can I say? Then A, P is really A, V1 through Vn, which by definition of matrix multiplication is A of V1 down to A of Vn, like so. And now since they're eigenvalues, this is going to be a lambda 1 V1, columns all the way down to lambda n Vn, okay? And now, of course, if I want to scale a column, I have to multiply by an elementary matrix on the right. So what this is this is exactly equal to V1 down to Vn, and then a matrix, lambda 1, lambda 2, lambda n, a diagonal matrix like that. And this diagonal matrix over here is going to do what? It's going to scale the first column by lambda 1, scale the second column by lambda 2, et cetera, et cetera, et cetera. So that's a diagonal matrix over here. So we've just proven over here that A times P is equal to, this is of course is P, so this is really just P times this diagonal matrix, the diagonal matrix with entries lambda 1 through lambda n. And therefore this gives me diagonalization because this allows me to multiply by P inverse. Since they're linearly independent, P has an inverse. And so this says that A will be equal to P times this diagonal matrix with entries lambda 1 through lambda n times P inverse. And this is what's referred to as diagonalization. So this is our diagonalization result. Oftentimes written as A is equal to P d P inverse. And of course, the one immediate consequence of this, which we get for free, is that if I raise A to any power k, that in general, that's very difficult to compute because A may have non-zero entries. But what we can do is we can write P d P inverse, P d P inverse. And of course, this is true under the assumption that the eigenvalues are distinct and the eigenvectors are linearly independent. So we have to check these conditions carefully. All the way down to what? P d P inverse, and then P d P inverse, right? And now the key to this is that all of these P inverses are right next to a P, right? So all of these intermediate P's and P inverses are going to cancel out, and you're just going to have P diagonal matrix to the K, P inverse, and that's very helpful because the diagonal matrix to the K is just the kth powers of the diagonal entries. So this is going to be diag of lambda 1 to the K, lambda n to the K times P inverse, right? So I'm able to get powers of the matrix for free if I'm able to diagonalize the matrix, right? So it's a very important question when we can diagonalize a matrix. Let me show you an example of how this actually works in practice, right? So here's an example. And my matrix A is 1, 1, negative 2, 4, right? Then this implies the eigenvector equation is determinant. The eigenvalue equation is 1 minus lambda, and then a 1, and then a negative 2 and a 4 minus lambda. Set that equal to 0 over here. And so when we solve this, we're going to have a lambda minus 4, a lambda minus 1, and then a plus 2 is equal to 0. So this is really lambda squared minus 5 lambda. And then I have a plus 4, that's a plus 6 is equal to 0. So we have a lambda is equal to what? Lambda is equal to, let's see. So I have a negative 2 and a positive 3, so 2 or lambda equals 3 will work. Great. Okay, and so what's the eigenspace for corresponds to 2, right? So if I subtract off 2, what's our eigenspace going to correspond to? So of course lambda is equal to 2. So when lambda is equal to 2, we're going to subtract off 2. We're going to have a negative 1 and a 1, and the second equation will be redundant, a negative 2 and a 2. We augment this with zeros, and we see over here that the eigenvector V is just going to be what? It's just going to be a 1, 1, okay? And then when lambda is equal to 3, what's our problem going to give us? Our problem is going to give us a negative 2 and a 1, right? When I subtract off 3, then a negative 2, and I subtract off 3, I get a 1, and we augment with zeros here. And over here we see we can take a vector W to be what? To be probably just 1 and then a 2. That will work. Great. And so now we can write our factorization of our matrix, right? So our matrix A over here is going to be 1, 1, negative 2, 4 is equal to the it's going to be the P matrix. The columns have to be the eigenvectors. So we're going to have what? The first column is going to be 1, 1, then a 1, 2. And then my diagonal matrix D is what? The first eigenvalue was 2. The second eigenvalue was 3. Great. And then the inverse of this matrix over here. So typically it's difficult to do an inverse of a matrix, but this one is simple. I'm going to flip the diagonal entries, negate the off-diagonal entries, like that, and divide by the determinant. The determinant is 2 minus 1 is 1, so there's nothing to divide by, so we have our factorization here. So it's a good exercise to check that this factorization actually works. But again, you might say, well, why would you want to do this? This is our first example of a matrix factorization that is actually useful in computing power. So this is a matrix factorization. And this matrix factorization is useful in computing powers of matrices. We'll see other matrix factorizations in this course will allow us to do other sort of algebraic varieties to matrices that help us in different ways. But this is a very, very powerful tool, but it's important to check that your eigenvalues are distinct. Distinct is only important in the fact that the eigenvectors are linearly independent. You can allow for repetition of the eigenvalues as long as the eigenvectors form a linearly independent set. Thank you very much.